Hello, everyone. My name is Josh. Welcome back to the Materials 2D03 thermodynamics and phase diagrams and alloys. My name is Josh, and today we're going to be going over some phase diagram basics along with the Gibbs phase rule. If you watched my last two videos, those two videos were kind of videos summing up what you would see on a first and second midterm of this course. This video here is going to be the first initial part of what you might see past those two midterms on an exam, maybe. These next couple videos are going to be very theoretical, so they're going to be shorter. I'm going to try to keep them to around 15, 20 minutes. If I go over, I do apologize. But yeah, this one should be a little shorter. Very, very basic stuff. Some stuff that you should already be familiar with up until this point. So we're starting off very easy with this video. So, phase diagrams. What is a phase diagram? Well, you can see I have a few right here. These two are binary phase diagrams. They split up our mixture of two different metals into different temperature gradients, and across these different temperature levels, not really gradients actually, sorry about that, temperature levels, across these different temperature levels, we can see that the mixtures create different phases. And these phases correspond to different liquids, solid liquid phases, and whatnot. So let's get right into things. So the first thing I want to talk about is the solidus and liquidus line. The liquidus line is right here. The liquidus line is the line where the first solid forms or where the last solid goes away, depending on where you're coming from. If I'm coming from this direction, the liquidus line, when I hit it, the first solid forms there. If I am coming from this way, when I hit the liquidus line, that is when the last solid leaves the system. The solidus line, again, depending on the direction I'm coming from, it can be where the last liquid freezes, or where the first liquid forms. If I'm coming from this direction, the solidus line is where the first liquid forms. If I'm coming from the direction of the red line, the solidus line is where the last liquid in the system freezes. Now, if we go to these temperatures marked off by the dotted lines, and we talk about Gibbs free energy, if we're looking at this area here, what can we say about the Gibbs free energy of the liquid compared to the Gibbs free energy of the solid? Well, we know we have all liquid, and we know that in equilibrium, the state that is in equilibrium, the state present, has the lowest Gibbs free energy. So we can say the Gibbs free energy of the liquid is less than the Gibbs free energy of the solid. Let's do the same trick down over here. The solid is in equilibrium, so we can say the Gibbs free energy of the solid at this point is less than the Gibbs free energy of the liquid at this point. Now, what happens over here? Well, that's different. Over here, we have solid and liquid. But we know that the Gibbs free energy has to be at a minimum when we're in equilibrium, when we have something. But we have both. So we can say the Gibbs free energy of the solid is equal to the Gibbs free energy of the liquid. Now, this is a very important thing that I'm about to say. When two phases coexist, the partial molar Gibbs free energy of each phase are the same. So when two phases are present at the same time, they are going to have the exact same partial molar Gibbs free energy. In this example, let's say for nickel, the partial molar Gibbs free energy of solid nickel is equal to the partial molar Gibbs free energy of liquid nickel. Now, what can we say about that? Well, we know that partial molar Gibbs free energy, we'll keep going with nickel there, that's equal to RT ln of the activity of nickel. So if the Gibbs free energy of nickel in the solid state is equal to the partial Gibbs free energy of nickel in the liquid state, we can say the activity of the nickel in the solid state is equal to the activity of nickel in the liquid state. This is very, very important. Keep this in the back of your mind. If you watch another one of these videos, you're going to see how we're going to use this. When a solid is formed underneath the liquidus line, let's remember what the liquidus line is. It's where the first solid forms. It's right here. When a solid forms underneath the liquidus line, the solid that is formed is at the composition that creates the lowest Gibbs free energy. So if our overall composition is in this phase diagram is around about 10 or 11, and we are in the alpha liquid region, we know that this composition of alpha at around 3% copper, and this composition of liquid, which is around 20% copper, this alpha solid and this liquid are at the composition which together minimizes the Gibbs free energy. Now, we still have to be at 10% composition of copper. How are we going to achieve this? Well, it's determined by the amounts of alpha and copper, which that is determined by the lever rule. If we want to find out how much alpha there is, what we're going to do is we know, determined by this line, this dot here, the closer and closer we get to alpha, the longer this line is going to get. The closer our dot moves, can I use this, please? Whatever. I wanted to use the highlighter or the laser pointer. Anyways, the closer this line moves towards the alpha region, the closer that line moves towards it, the more alpha we have, meaning this line grows bigger. So we're going to take the length of that green line, and we're going to subtract it by where our dot is. We're going to divide this value by the total length of the line. So actually, we're going to take the length of the green line. Sorry, I drew that calculation wrong. We're going to take the length of the green line, which is the liquid composition, minus our dot composition. And we're going to divide it by the total length of the line, which is our liquid composition plus our solid. Nope. I don't know why this is blanking for me right now. The total length of this line is going to be, yes, liquid comp minus our solid comp. Sorry about that. That will give us our amount of alpha that we have. Beautiful. From here, let's talk about the Gibbs phase rule. I'm going to use this graph again. So the Gibbs phase rule is something that tells us how many degrees of freedom we have in our system, how many variables we can change while staying in one phase. Here, we're going to let C be equal to the number of species that we have. We're going to let P be equal to the number of phases. And we're going to let F be our degrees of freedom. If we were to have a phase diagram that only has one species, right? We would have a changing variable of pressure and temperature. So if we were to write our variables for one composition, we would have our C. We would have our P variable for phases, which is our number of phases. And we would have temperature and pressure. In total, the number of variables we have are going to be P, our number of phases, multiplied by our composition, plus temperature, plus pressure. Now, if we're just to be considering an arbitrary number of variables, not for this anymore. So let's consider the number of variables that we have. In any given system, the number of variables that we have are going to be equal to the number of species. Since we know we can find out the number of species by taking the actual number we have and subtracting it by 1, so we have C minus 1, we can do this because if we were to be given XA and we were to have it composite a mixture of XA and XB, we can find XB by taking 1 minus XA. So however many species that we have, we can find out the last one through algebra. We also have each phase, and we have temperature and pressure. Each phase, so number of variables, corresponds to each phase multiplied by the composition and the temperature and pressure. Temperature and pressure are always there, so those can just be the number 2. We're going to add that to our composition, C minus 1. So we get C plus 1 for our number of variables. For our equations, each type of variable is going to have P minus 1 number of equations. So for our number of variables, for number of equations, that's going to be equal to how many variables we have? Well, we have C plus 2 variables multiplied by P minus 1. To get our degrees of freedom, we're going to take our number of equations, or our number of variables, minus our number of equations, which is going to give us C composition plus 1 minus P number of phases. Sorry, not C plus 1, C plus 2. This is for one composition system, because we can consider both P and T. But in 2 binary systems, we have to consider only temperature as a constant one. So we can have C plus 1 minus P for binary. Well, let's use some examples. We have a binary system here. If we were in this bulk phase, what is our degrees of freedom? Well, how many species do we have? We have 2 species plus 1. We're in one phase, so we have 2 degrees of freedom. We can change temperature and we can change composition. What about right here? Well, we have 2 species plus 1. We are within 2 different phases, the liquid and the theta plus liquid phase. And that is a minus. So we have 1 degree of freedom. If we change the composition, the temperature is going to change with us. If we change the temperature, the composition is going to change with us. What about for right here? Well, we have 2 species plus 1. We have 3 phases, so we have no degrees of freedom. Something that you might encounter is if you have reactions. So in this calculation here, we're considering no reactions. Considering reactions, our C is now going to be equal to the number of species minus the number of reactions that we have. But that is if specified. All right, thanks for watching. Come back for another video where we're going to be talking about the miscibility gap. Thanks.